With the if charts, there's a feature that the book includes that I kind of like. Ooh, I'm going to try something new here. Give me a second. I think that I can do insert space. Oh, I was hoping I could just go right down the middle, but I can't. That's lame. We'll just stick to drawing. Your textbook. Whoa, buddy, what'd you just do? Your textbook includes a thing in between the I and the F, okay? Because the I is what happens before the internal interaction. The F is what happens after the internal interaction. So in between those, they include a graph, as it were. Not of velocity and mass, but of force and time. How's that pink working for you? Let's switch that up. Yo, buddy. There we go. So if I have my I, this is velocity, this is mass. I have my F, this is velocity, this is mass. And then in between, they're including the impulse. And that's as a graph of what we would call unbalanced force versus time. And that unbalanced force could be directed positive, could be directed negative. If we're dealing with situations with collisions, which is a lot of what we've been looking at in class, then one of them is going to feel a force in the positive direction. And so I'd maybe represent that like a rectangle here. And the other is going to feel, as we talked about, I think yesterday, as much force. Let's count here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's going to feel as much force in the negative direction. And so I'd represent its impulse by this blue rectangle, okay? That's going to have the newtons. The newtons? Help me, Ol. That's going to have the units, Newton seconds, which is equivalent to kilogram meters per second. So over here, your area is kilogram meters per second. Over here, your area is kilogram meters per second. The long story short of this, if it's some kind of a collision, is whatever positive impulse the one has, the other's going to have the negative of that. And so the net change in the end is zero. That's why we have conservation of momentum, if they're just interacting with each other. This shows up in some of the mastering problems. They'll give you some kind of a graph of force versus time. But rather than, they might give you a rectangle if they're feeling nice. Okay, but a lot of times these are going to have the shape of like a trapezoid, or maybe they'd be just a triangle of sorts, something like that. And the long story short is that the area here on this graph equals the impulse. Okay, and impulse equals change in momentum. So the unit's Newton seconds, equivalent to kilogram meters per second. All right. All right. Moving on. You would, and so that's why with this graph, this axis here is time. So it'd tell you the base of the triangle or the base of the rectangle, and it'll allow you to figure it out. So this example here with the red and the blue, I'm saying is if there was a collision, the one's going to feel the force in the positive direction, the other feel it in the negative direction. It's going to act for the same time for both of them. So that's why in collisions, the changes in momentum kind of balance each other out. But you could certainly have a situation where you were given like the change in momentum for the object and some aspect of the force, and maybe you'd have to solve for the time. So you'd know the change in momentum is the area of the shape, and the force might be the peak of the triangle, and then you got to figure out the base of it. But it's a lot of the same reasoning we've been doing with graphs all year. All right. I'm going to pivot that over here to this thing with splosions. And I have these images kind of blown up in the back. It's on Canvas if you want to have it in front of you. Okay. And what you're looking at is this. I've got these two carts here, and we're going to make use of the little spring-loaded plunger bits that are on there. Okay, right now the spring is compressed, but then when I give this thing a tippity tap, ooh, that's pleasing. Okay, so right now I've got the cart centered at 60 centimeters, and it's a 120 centimeter long track. Ooh, right? Okay, so pop on over to the old, what are we doing here? Pop on over to, oh, hey! But you got to say it right, though. Can you kind of make it kind of Valley Girl? Crab. Like, put a little fry on there, something like that. Crab. All right, so there you go. Joinpd.com, crab. Last hour it was envol, which we said would be like if you had an oval-shaped navel. No? Crab. All right, and over on this crappy pear deck, I'm looking for you to tell me, what'd you notice here, friends? Oh, man. Oh, boy. All right, let's start blasting through some of this stuff here. So they hit the books at almost the same time. They had the same amount of force pushing on them, pushing them back. Equal momentum in opposite directions. They're not moving. Both are rest on a frictionless surface. Then when another force acts on both of them, they both move with equal but opposite velocities. Explosion was created by one cart exerting a force on the other, which didn't have any support. Now, hey, be a little physics cautious here. Was one cart exerting a force on the other, or were they interacting here? Okay, if we drew free body diagrams for each of these things, you look at the outcome here as well. I would assert that that there was a force A comma B and an equal size but oppositely directed force F B comma A. Okay, so they're interacting with each other. Hit the book same time, meaning they have the same velocity. Thoughts on that statement? How might we modify that? Opposite velocities. Okay, if one has velocity v, the other has velocity negative v. Be really cautious about this, okay? It's intentional that we're taking mass times velocity here, not mass times speed. The direction matters. So sneaky physics teacher tricks to look out for is like a ball is thrown at a wall with a speed of 30 meters per second. It bounces off the wall with a speed of 20 meters per second, okay? That's not a change in velocity of 10, that's a change in velocity of 50. If it's going 30 one way, now it's going 20 the other. So be really mindful of how direction plays the same in here. Is Danny Roundpot in here again? They had the same velocity, just different signs, and stopped around the same time. They also both started at the same time. Quantum electrodynamics. Carts hit the book at approximately the same. Blah, blah, blah. Yeah. Okay, cool. So we're all on board with that. All right. And I think somebody mentioned in here the thing about the masses, right? And you see that if you look really close at the image on canvas, you can kind of read the masses. This one is 0.496, and this one is 0.497 kilograms. I screwed it up, and they were like different by about 60 grams, and it mattered. but now I picked carts that are pretty close to the same mass. So, and I should point out a couple other things in the image here. If you look really close at this one on canvas, it's centered at 60. The track's 120 centimeters long, but the total distance traveled is not 120 centimeters. The front of this cart is at 77. The front of this cart is at 43. Okay? So be mindful of that, because what I'm going to do now is add a bar that's about 497 grams. I'm going to add a bar to this cart, the one that's closer to 0. Okay? And then if I do that and I hit the thing, oh, that's not pleasing at all. Okay? So help me with the layout here. But again, be mindful of this stuff. Okay? That the let me point this out again. Where's my pink? Okay? The front of this one was at 77 centimeters, when the front of this one was at 43 centimeters, when they were centered at 60 centimeters. Okay? Where do I want to center it now so that they... Where do I want to center it now so that they both will again hit the ends at the same time? And again, Mr. Harding, what did you change? I changed it up, so this one's now going to have a mass of basically 1.00 kilograms. So the bar is effectively the mass of the cart. So one of them is now M, one of them is 2M. The Pear Deck is eagerly awaiting your numerical answer. And again, that's where they're at on the track. So the more massive one is closer to 0, the less massive one is aiming towards the 120 centimeter end. Some of you are overly optimistic on the precision with which I can place these carts on that track. Hey, numbers wise, like here's what I'm seeing. Okay, there's kind of a spread. It looks like the average right now is somewhere around 40. It's varying. Okay. So what I would advise you to do is consider the information I'm giving you about the initial situation. I'm not sure everybody's taking that into account. They're centered at 60, but the total distance traveled is not 120 centimeters. The front edge, the edge of this closest to the book is 43 centimeters. The edge of this one, which is closest to the book, is at 77 centimeters. So make sure you're taking that into account. I think it looks like everybody's kind of using the same reasoning, but we're still seeing a spread on the answers. And again, it does tell me up here who's putting what in, so do be mindful of that. Don't be donkeys. All right, so at the moment, it looks like the average is 40, okay? Some have 30, some have something around 46, but it's averaging out around 40. It looks like there's a clustering of numbers there. Let's check that. We're kind of checking the answer before we're really talking through the reasoning. But I'm going to put it here at 40, and let's see what happens. Maybe. Let's try that again. So here it is. This is 40 right here. So here's 0, here's 120. I don't think that's working. So if you're 40 or less, run that by your neighbor, kind of what your rationale is. And again, I'll throw this up here. Are you incorporating the information that I'm sharing with you here?
have no idea. I got one equation and I'm trying to like make a second one.
This is like something with these need to be the same. And this is 1 kilogram. This is 0.5.
Yeah.
So like 0.5, we'll call this going that way is velocity x plus we'll call the one going this way, which is, or actually that's going slower, so
yeah, x plus 1, x plus y, if it's like f second is y. Yeah, that's right. No, because the way it works out is that the area of this plus the area of this has to equal 0.
yeah.
So x-axis times this velocity plus x-axis times this velocity.
All right. You picked up what some of your friends were putting down, and now, or you're guessing and checking. That's always a possibility. But it looks like we've had a narrowing, okay? And now the average is 46, and the range is, a lot tighter. So let's try that. Okay, so I'm going to center it at 40. Let's see, what was it again? Yeah, I'm going to center it at 45.66666666. Okay, and see how this shakes out for us. Ready? Shh, shh. So pleasing. Okay. So now let's go back and talk about the if chart. Now that we know that works, and we'll just kind of run this proportionally. So I've got my I chart and I've got my F chart here, and let's stick with this backwards theme. Okay. So M is going in the positive direction, and 2M is going in the negative direction afterwards. So if I give M I don't know. How many blocks tall do we want to make this? You can't see it? Is my heat in the way? On the if chart. So how tall do we want to make this? 4 tall? 1, 2, 3, 4. Okay. So if I make the velocity of the M glider V, what has to be the velocity of the 2M glider? Run it by your neighbor. Be really cautious about how you're saying it. Should it be negative V? Why negative V over 2? So, hey, shoosh, people. Emma's going to do that talking thing. What do you got, Emma?
Because the negative 1/2, like you can take the negative 1/2 and then the 2 from the mass as coefficients, and if you multiply them together, it cancels out the negative 1, which needs to be the opposite, like they need to have opposite but equal momentum. Yeah.
Okay. So up here, this is MV. And down here, you shake out the math, you get negative 1 MV. And like the reasoning's kind of already there, but the long story short was prior to the explosion, M had a velocity of 0, 2M had a velocity of 0. So the initial total momentum would have been 0 kilogram meters per second. So the final total momentum is 0 kilogram meters per second. And the reason for that is the only interaction that's happening here to change momentum is within the system, FA, B, FB, A. And if that's the case, we should have the same total momentum after the incident that we had prior to it. It's an interaction that's internal to the system, so momentum is conserved. Okay? So that's kind of how you deal with explosions. There were some questions earlier. I spoke with a couple people about the mastering and the problems on the if charts worksheet, and it's a little bit what do I want to say, like trying to establish when is I and when is F. Those things straddle the interaction. Okay, the interaction is the explosion, so I happens prior to the explosion, and F happens after the explosion. Or if it were the air tracks the other day, I happens prior to the collision, F happens after the collision. Okay? Yeah.
Like from there, you just plug that in, or how do you find like 46?
How'd they find the 46 centimeters? The total distance traveled is not 120 centimeters. What are you using for that? Let me throw another numerical question your way. What's the total distance? Oh, let me re-ask the same question. Come on, Pear Deck. All right. Number answer. All right. What's the total distance traveled? Not 120 centimeters. What do you get? Total distance traveled. There you go. 86. Okay. And where does 86 come from? This is 120 centimeters in total. But from card end to card end, this is 43, and that's 77. So they're each 17 centimeters. So you got to subtract the lengths of each card out of that 120. And so 120 minus 17 will give you 86 centimeters of total distance traveled. And then proportionally here, since the one is twice as fast, we need to make it have to travel twice as far as the other one. So it's going to take 2/3 of that 86, and then this one's going to take 1/3 of that 86. And that'll kind of help you establish where you're going to set them. And so we're going to set them this time at 46. And if you center it at 46, then the chubby one's going to travel 1/3 the distance of the skinny one. All right. So let's close out of this. And then what I'm going to do, I can just